We just had a discussion in the last video dealing with equilibria of weak acids and weak bases. Well, now we're going to look at what would happen if we were dealing with salts. Now remember, a salt is simply an ionic compound made up of a metal and something that's acting as a metal and something that's acting as a nonmetal. It can be a metal and a nonmetal. It could be polyatomic ions acting as a metal or a nonmetal, but you've got one of each. If we have a neutral salt, now we've always, perhaps in earlier assignments when you were looking at salts and you were talking about whether something was acidic or basic or neutral, we've pretty much said that salts were neutral. Well, they're not all exactly neutral. Now, there are neutral salts, and neutral salts are formed when you have the cation of a strong base and the anion of a strong acid coming together to form the salt. And they will indeed be a neutral solution when they're dissolved in water. Sodium chloride is an example of this. Now, when I say the cation of a strong base, Na is the cation of the strong base NaOH. Chloride is the anion of the strong acid HCl. We just add normally OH to the metal and get the base. We put H in front of the nonmetal to get the acid. So both of those are strong, so we end up with a neutral salt. But we also have what are called acidic salts. Acidic salts contain, they're formed from the cation of a weak base and the anion of a strong acid. So an example of that would be NH4Cl. We often call that a salt of a weak base because we're always going to focus on what part of it is from a weak parent acid or parent base, if you will. Take NH4Cl, for instance. NH4Cl, the NH4 results when we started with NH3 as the base, and it was a dirty, nasty hydrogen stealer and became NH4 plus. So the parent is NH3, and that is a weak base. The parent acid is from the Cl. Remember, we add the H in front of the nonmetal, and we get HCl. So it's got the strong acid parent, a weak base parent. What that ends up being then is the strong overcomes and we get an acidic salt. And you can just look at the formula of these salts and you can tell based on what the parents were, the parent acid and the parent base, whether they're neutral salts, acidic salts, or as we'll see in a moment, a basic salt. So let's look first at what happens when we have this acidic salt dissolve in water. What happens is that when we dissolve this in water, water will attack the weak, the part that's from the weak parent, in this case, weak parent base. So water is going to attack the NH4 plus. We call it hydrolysis. It's going to hydrolyze that NH4 plus. It's going to again attack, and this is what we get. We get the NH4 plus reacting with the water, and what happens is, since that NH4 plus is weak, it's going to donate its hydrogen to the water. We're going to end up with NH3 and H3O plus, and that H3O plus that we end up with after water attacks is why this is an acidic salt. Now I want to move on down to the bottom then, and let's look at what happens with a basic salt. Okay, with this basic salt, what we have is the cation of a strong base and the anion of a weak acid. So look at its parents. The parent base is going to be NaOH, and remember, sodium hydroxide, group 1A hydroxide, is strong. Our parent acid is HF, and remember HF, hydrofluoric acid, is the only hydrohalic acid that is weak. HCl, HBr, HI, they are all strong, but this one is weak. So since we have a strong base parent, this is going to be a basic salt. When it dissolves in water, or splits as we have often called it, we end up with Na plus and F minus. And remember, water attacks the weak. So water is going to attack the weak part of that, and the weak part is this F minus. That's the weak parent, HF. So what happens? Well, we've got that F minus that comes down here and reacts with the water, sets up an equilibrium. The only thing that can happen here is for that F minus to grab hold of a hydrogen from water. So we get HF forming, but look what's left behind. We leave behind that OH minus. And that OH minus is what makes this a slightly basic solution, a basic salt. Now you're going to have a worksheet where you have to come up with these equations. So I want to do the first three on the worksheet together. You're responsible for the rest of them, but let's look at this. The first thing you have to decide is whether you're dealing with an acid, a base, or a salt, because it's going to determine how this reaction is going to work. If it's an acid or a base, a weak acid or a weak base, then you're going to write just a normal ionization reaction. HF, for instance, we'll start with HF. It's weak, so it does not split. Remember, weak acids do not split. We're going to react it with water. And since that's a weak acid, we've got to label it as an acid, a salt, a base, or a salt. That weak acid does not split, and we're going to end up with that acid giving away its hydrogen very nicely, and we end up with F minus. That looks like plus, the way I wrote it, but let's rewrite that. F minus plus H3O plus. So there's the reaction for this one. And that is a weak reaction, by the way, so it should have an arrow, an equilibrium arrow. Now on this next one, NaCN. Na is a metal, Cn is a polyatomic ion acting like a nonmetal. This is a salt. And the salts that we'll be dealing with in this area of chemistry are going to be soluble salts, so this is going to split. And what we end up with is Na plus and Cn minus. Now it's important for you to know this and to realize that these salts are going to split and dissolve. They're going to be soluble in water because we have to pick the weak part to be attacked. Remember, water is going to attack the weak part of a salt after it ionizes in the water, after it dissolves. Na is part of NaOH. It is strong. Water can't attack it. But Cn minus is part of HCN. That is a weak acid, so that's what water is going to attack. So we're going to take the Cn minus, show water attacking it, and when water attacks it, we're going to end up with HCN, and we're going to leave OH minus behind. So that's going to be a basic salt. A basic salt. Finally, the last one we're going to do together is NH3. NH3 you have to memorize, but I expect you to know by now that it's a base, and I expect you to know it's a weak base because it's not a hydroxide. Only the hydroxides of groups 1A and 2A, except for magnesium, are strong. So this is a weak base. So is it going to split before it reacts in water? No, it is not. It's going to stay together as NH3, react with water. And remember, bases are dirty, nasty hydrogen stealers. So it's going to form NH4 plus OH minus. So those are an example. I've shown you an example of an acid, a weak acid in water, a salt in water, and a base in water. So I expect you to be able to do the rest of these problems on this worksheet in a similar manner. So I wanted to go over that very quickly before we go back and pick up some more information with our salts. Okay, the next important piece of information is that you cannot find the Ka of NH4 plus in a table. However, it does have the Kb of NH3, and NH4 plus and NH3 are conjugate acid-base pairs. Very important thing to know. The Ka of the acid in a conjugate acid-base pair times the Kb of the base is 1 times 10 to the minus 14th. We've seen that number before. If that's true, then if we want to find the Ka of NH4 plus, we have to know it, then the Ka of NH4 plus is going to be 1 times 10 to the minus 14th divided by Kb, right? So 1 times 10 to the minus 14th divided by Kb, which is 1 times 10 to the minus 14th divided by, and it gave us that value right up here, 1.8 times 10 to the minus 5th. So the Ka for NH4 plus is 5.6 times 10 to the minus 10th. You're going to have to do that multiple times. If you're dealing with a salt equilibrium problem, you are always going to have to find the other K value. Find a new K value. Okay, so let's look at this next one. Find the Kb for F minus if the Ka is 7.2 times 10 to the minus 14th. We've already established that all we have to do to find the new K for a salt ion is to take 1 times 10 to the minus 14th and divide it by its conjugate acid or base pairs equilibrium constant. So I'm going to divide that by the 7.2 times 10 to the minus 4th that it gave me here. And I end up with a Kb of 1.4 times 10 to the minus 11th for the new Kb of F minus, which again, you can't find those ion K values in a table. So how does this play out in a problem? Let's look at this. It says calculate the pH of a 0.15 molar solution of sodium acetate. We're getting more and more different kinds of equilibrium problems, and it's going to be incredibly important for us to now start making sure that we know what kind of substance we're dealing with. Sodium acetate, Na with CH3COO or CHO232, C2H3O2. Either way you choose to write acetate, that is a salt. And as soon as we know it's a salt, we know that it's going to split when we dissolve it in water, and water is going to attack the weak. Is Na plus going to be the weak part of that ion? Remember, Na is the weak, excuse me, Na is the parent is NaOH. That's strong, so that's not going to be what water attacks. Water is going to attack the CH3COO minus, because that's part of CH3COOH, which is acetic acid, which is weak. So that's the reaction we've got to show. That's why it was important for me to show you how to do those reactions that on that worksheet. So water's going to attack the weak part of this, which is going to attract a hydrogen, take a hydrogen away from the water and leave OH minus behind. So there's my reaction. We just said it was 0.15 molar solution. Remember, this splits, so it's a soluble salt, which means if we have 0.15 molar solution of sodium acetate, we have 0.15 molar sodium and 0.15 molar acetate. So our initial concentration is 0.15 molar for the acetate. Now, water, remember, we don't care because it's a pure liquid, and that doesn't get involved in the equilibrium expression. We start out with 0 for both of these. Our change is minus x plus x plus x. So we get 0.15 minus x, x, and x. We set up our equilibrium expression just like we've been doing, and we get that the K, now remember, CH3COOH is the acid, so what's CH3COO minus? That's the base. KB is going to be CH3COOH concentration, products over reactants, times the OH minus divided by the CH3COO minus. So there's our equilibrium expression. And here's the problem. We don't have a KB of CH3COO minus. So how are we going to find that? We're going to do what we just did on the previous page. If we want to get that new K, then we're going to take 1 times 10 to the minus 14th divided by the old K, which was 1.8 times 10 to the minus 5th, which gives us a KB of 5.6 times 10 to the minus 10th. So there's our new K, and that's what we're going to have to use in this equation. So coming down here, that's going to give us 5.6 times 10 to the minus 10th. And that's the only thing that's different about a salt equation or a salt equilibria. You've got to get that new reaction, and then you've got to find a new K. So our equilibrium concentration for both CH3COOH and OH minus are x, so x squared over 0.15 minus x, which is approximately equal to x squared over 0.15. X squared, when we multiply 0.15 times 5.6 times 10 to the minus 10th, we get 8.40 times 10 to the minus 11th. And if that's x squared, then square root that, and we'll get a value of 9.2 times 10 to the minus 6th. And that's a molarity. Molarity what? Make sure you pay attention. In this equation, X is the concentration of the hydroxide ion. So we can now get POH by taking the negative log of that hydroxide ion concentration, which gives us a POH value of 5.036. I've got more sig figs than I need, but I don't want to round too much till I get to the end. Remember, pH then is going to be 14 minus POH, which is going to be 14 minus the 5.036, and we end up to the 2 sig figs that we need. Remember, they don't count until they're after the decimal. 8.96 for the pH of this solution. So again, the only thing you do different, you get that equation and you find a new K, and that's the only difference in our salt equilibria.